moment of inertia. Now this moment of inertia is nothing but it is related to rotation of a body, and this is nothing but the inertia of rotation. Rotational motion. As we say, the momentum is the inertia of linear motion, actually it is rotational motion. Yeah, so here in the case of momentum it is inertia of linear motion, while it is moment of inertia represents the inertia of rotational motion. And assume that this is a massive body, irregular, and somewhere here we have a point at which the whole mass of the body is assumed to be concentrated. Now and I'm drawing some line over here over which I am rotating this body, and this is the center of mass. Now center of mass is nothing but the point at which the whole mass of the body is concentrated, and the moment of inertia I, the moment of inertia is given by I is equal to mk squared. Now what is this k? K is the perpendicular distance from the axis of rotation. This is axis of rotation. So it's the perpendicular distance from the axis of rotation, and this is called k is radius of gyration. Now here we are seeing the circular ring with a radius equal to capital R. So this is the center, and this is the radius of the circular ring, and the axis of rotation is passing through the center. Okay. Now then the moment of inertia I is equal to mr square. That is, you can write this as if it is a z-axis, that means the circular ring is in xy axis. So this is something like this. This is x and this is y. This here you will have x-axis, this is y-axis, and this is z-axis. So circular ring is placed on xy axis, and along the z direction we are finding out iz, which is equal to mr squared. Now in another way, we can also rotate the circular ring in this form. That means if you consider this as the diameter of the circular ring, this is the diameter uh, from here to here. That means along the diameter you can write ID is equal to mr square by 2. So the moment of inertia along z, that means perpendicular to the plane, and here it is parallel to the plane, that means along the diameter. So here this is perpendicular to plane. What is the plane here? Plane is nothing but xy plane. Now here it is parallel to xy plane and along diameter. So parallel to xy plane along diameter, ID is equal to mr square by 2. D represent the diameter. Here we have the circular disc and the radius is r, and the same way here also we have the center here, and this is the radius, this is x-axis, this is y-axis, and this is the z. So moment of inertia, when you have a rotation here, it is Iz is equal to mr square by 2. Okay. Now when you write down the radius of gyration k, so Iz is equal to mk square, we can write k is equal to r by root 2. So plus or minus r by root 2, that is radius of gyration. Now when you place the disc along the diameter, that means the rotation is along the diameter, so this will be the rotation. Now here this will be the rotation. Okay. When you rotate this disc, you will feel that it's a sphere. So this is how it is rotated, and ID along the diameter, ID is equal to mr square by 4. Here also you can write down the radius of gyration k, which will be r by 2. Now this is a rod of length L, and you can rotate this in two ways. This is the center of the rod, which will be at L by 2, and here you can also rotate with the L. So this is 0, this is L, 0, this is L. So in this way, if you rotate, the moment of inertia I is equal to m L square by 12. So this is the moment of inertia in the first place, and here on the right, then the moment of inertia I will be equal to m L square by 3. So this is the axis of rotation here, and now here we have, this is the axis of rotation. Now this is hollow sphere, and here we have solid sphere, both with radius R equal to capital R. This is R equal to capital I. So this is now along the center. This is center. If you rotate the moment of inertia, this rotation is always along the diameter, because anywhere if you draw a line connecting two ends of sphere, it would be the diameter passing through the center. So ID is equal to 2 by 3 times mr squared, and here ID is equal to 2 by 5 mr squared. Perpendicular axis theorem. Now let's assume that this is a plane lamina, and perpendicular axis theorem is always applicable to plane lamina. And this plane, assuming that it is in X, this is Y, and this is Z, the perpendicular axis says that Iz, that means the moment of inertia when rotated along the Z direction, that is this, will be equal to moment of inertia when rotated along the sum of the moment of inertia. Now you rotate it like this and like this, so you would get two moment of inertia, which is Ix and Iy, and Iz will be equal to sum of the moment of inertia when rotated along X direction and Y direction, that means in the plane. Okay, and this Iz is perpendicular to plane XY, and this both are along the plane. Now, understanding the perpendicular axis theorem in terms of perpendicular axis theorem for circular ring, theorem for circular ring, we have, let this be 1. We know that this is along Iz, this is equal to mr squared, and this is Iz, this is Ix, and this is Iy. So Iz is equal to Ix plus Iy. Now Iz is equal to mr squared, and you know that Ix is equal to Iy because both are along the plane, so you can write it as Ix, that means it is along the diameter, so ID plus ID, so 2ID is equal to mr squared, and ID will be equal to mr square by 2. So this is what we have got in the previous session. So this is the proof for perpendicular axis theorem in terms of the same can be applied to circular disc. We are understanding through the perpendicular axis theorem. Now here we know that this is id, which is equal to mr square by 2, and this is ix, this is iy, and this is iz, and ix is nothing but id, and iy is equal to id, because it's along the diameter. When you extend this both are in same plane, so it's along the diameter of the disk. So you can write iz is equal to 2 times id, and iz is mr square by 2, that's equal to 2 times id, and id is equal to mr square by 4. So this is the moment of inertia in the plane lamina, that is x, y and z direction in the perpendicular to the plane. Parallel axis theorem. Now parallel axis theorem says, now suppose if you have this as the axis of rotation. Now this, let us write down this. What is this? This is axis of rotation at the center of mass. Okay, so axis of rotation at the center of mass, and now this is the axis of rotation made. So this is axis of rotation at the center of mass. We will center of mass, or you can write gravity. This we can write it as the id, sorry, let it be ig. Okay, so center of mass, this one. So this is moment of inertia due to center of mass at the okay. Now, and at a parallel distance, which is at a distance of d, we have another axis of rotation, and let us call this as I parallel. So I parallel is equal to the ig, which is from the center of mass or the center of gravity, plus m d squared. Okay, so we need to know ig. If you know ig, you will get I parallel. With the circular ring, we are going to find out the application of parallel axis theorem. So this is according to the parallel axis theorem. This is the perpendicular that we know. This is because this is center G and IG. Now when you rotate, you get IG equal to mr squared. Now actually this is not what we want. We want the I parallel. So this is exactly parallel to this axis of rotation here on the surface or on the perimeter of circular ring. This is circular ring. Okay, so mr square. So I parallel is equal to ig plus m d square. Now what is d? The distance of this. Since it is on this ring, we can write it as this is nothing but r is d is nothing but r. So this distance is d. So m d squared. So ig we already know it. It's equal to mr square, and m D is nothing but R squared. So I parallel equal to 2 times mr squared. So this is I parallel. Similarly, on the right we have the axis of rotation in this way along the diameter. So now this is IG, and at a very same distance, that is R, that is actually the D according to the parallel axis theorem. I parallel equal to ID plus or IG plus MD squared. And what is IG? IG for circular ring along the diameter is mr square by 2 plus this is mr square, and thus I parallel is equal to 3 by 2 times mr squared. Applying the parallel axis theorem, applying the parallel axis theorem to circular disc. Okay, so we know this is Iz. Now Iz, since it is along the gravity, that is considered to be Ig, and at a perpendicular distance on the parallel way, that is, this is the distance D, which is also the distance radius R. We have I parallel, and which would be rotating in this way, and I parallel is equal to Ig plus md squared. Now Ig is nothing but Iz for circular disc, which is equal to mr square by 2 plus md is nothing but r square. So I parallel is equal to 3 by 2 mr squared. Now this is this for along the diameter ID, and this is also equal to Ig for parallel axis. So I parallel, now this is the parallel axis, and at a distance R according to the parallax theorem, this is D. Now I parallel is equal to Ig plus md squared. Now what is Ig? Ig, we know it's Id, that's equal to mr square by 4, and this is mr square by 4 plus mr squared, because t equal to r, so this becomes 5 mr square by 4. So this is application of parallel axis theorem to circular disc around the circumference or the edge. And here we are applying the parallel axis theorem to thin rod. Parallel axis theorem to thin rod of length L. Now this is the moment of inertia along the center of mass, that is the Ig, and here we have I parallel, and I parallel, as we know, it's equal to Ig plus md squared. Now what is D here? The whole length is of L, and this is the distance from center to the parallel axis is L by 2. Now IG is nothing but through the center we know that it's equal to ml square by 12, so it's ml square by 12, so ml square by 12 plus d is nothing but L by 2, so L by 2 whole squared, so this gives us ml square by 12 plus ml square by 4, and just multiply by 3 here, so it gives us 4 ml square by 12, which is nothing but ml square by 3. So this is I parallel, and I parallel is nothing but we have already discussed about it, that is passing through edge.